All right, I think we can start. Welcome everyone. Welcome to this webinar on photothermal microscopy. It's my big pleasure today to chair the first session. The first speaker is Professor Ji-Xin Cheng. Professor Cheng is now a professor in photonics and optoelectronics at Boston University. This is since 4 years ago. He did his PhD at Hefei in southern China, close to Nanjing, 1998. And then he did a postdoc in Hong Kong, and he joined the group of Sunny Shi at Harvard in the years 2000-2003, where he developed nonlinear spectroscopy in microscopy, in particular coherent Raman and Rayleigh scattering. Then he took the job of assistant professor, and he went through all the grades at Purdue University in the Center US, and he stayed there from 2003 until 2017 before moving to Boston. So Professor Cheng has many awards and has received a lot of recognition. He has very important papers on the application of nonlinear optics to microscopy, especially in biological samples. He has very important papers in Science Advances. He has become, as you say, the editor of this journal recently. And he has too many awards to cite them all. He is a fellow of the OSA in particular since 2 years ago. And I'd like immediately to give him the floor, and I'm looking forward to hearing about his progress in photothermal mid-infrared microscopy. Please.
Oh, thank you, Michelle, for the nice introduction. It's my honor to be here today. I will present mid-infrared photothermal microscopy. So before that, I would use one slide to introduce my current research program. So my research is featured by label-free. So the major direction is label-free chemical imaging, which I'm going to present today. Since we moved to Boston University, we have two new directions. One is called a genetics-free neuromodulation based on optoacoustic effect. So this is to compare with optogenetics approach. We also discovered a method that it can kill a superbug by photobleaching this intrinsic chromophore, such as the golden pigments in MRSA. I disclosed financial conflict of interest to Vibronics, a medical device company, Photothermal, a phototherapy company, and also a photothermal spectroscopy cup, which is related to the research I'm going to present today. Of the many ways of doing label-free imaging, vibrational spectroscopy provides very rich information because chemical bond vibration provides a fingerprint of molecules. So this allows us to recognize specific molecules in a label-free manner. So in this review paper, we show that we can study protein synthesis to single-cell analysis in C. elegans all the way to the plaque diagnosis. Molecule vibration can be measured by infrared absorption or Raman scattering spectroscopy. These two linear spectroscopy has been widely used, but each of them have limitations. For example, we know that FTIR has suffered from strong water absorption, low spatial resolution. Raman spectroscopy has very low cross-section, which makes the speed too slow for imaging purpose. So over the past 20 years, and my group, along with others, has been developing this coherent Raman scattering microscopy based on either CARS or stimulated Raman scattering to boost the signal level and also much increase the imaging speed, which now allows many kinds of biomedical applications. So there are two books, one published, one in press. I will not go into details. So back in 2015, when I was writing this review article, we were thinking that what is the boundary of the field? And we realized that all in all, that the Raman imaging, no matter coherent or spontaneous, is limited by this very small Raman scattering cross-section. So we boldly think out of this Raman box. And there we have this infrared absorption, which has a cross-section 100 million times larger than the Raman scattering. And we believe that if we use infrared contrast, we can do vibrational imaging that can break the sensitivity limit in Raman microscopy. But actually the IR is actually complementary to Raman scattering. So in Raman spectroscopy, it's very sensitive to the CH vibration. So that's why CARS, SIs has been largely used for imaging lipid metabolism in cells. But when you go to infrared spectroscopy, it's super sensitive to the fingerprint region, such as ML1, ML2, the phosphate band at 1260 and the 1084 for the CO bond for the carbohydrate. So infrared provides very rich information about biomolecules. And infrared microscopy itself is a large field. So this is based on the Beer's law, the infrared absorption, and this can be implemented through FTIR microscope, or more recently through a QCL laser-based IR microscope. Yet this conventional approach suffers from the spatial resolution, which is a few micron, and we cannot see any details inside a cell, and we cannot apply this to do living cells because of water absorption. FMIR was developed in the last 2 decades to provide nanoscale resolution, but still the speed is slow, and this cannot look into a living cell. So a few years ago, we published a paper to break the diffraction limit in IR by IR pumping and visible probing. The idea is that we're using a dark field geometry. So in physics, the IR fitting will cause a local change of the refracting index and the thermal expansion of the subject. Then we can use a dark field geometry to probe this mid-infrared photothermal effect. So in theory, that the intensity change is proportional to the refracting index change and also the number of molecules in the focal volume. This allowed for the very first time that we can use IR to map a chemical bond in the living this is prostate cancer cell. This was not possible with conventional IR approach. In FDR, we would only see one spot for this whole cell because the size of cell is about 10 micron. We are not alone in this field. There are many other groups mentioned here also contribute to this field, especially you will hear the Greg Harland later in this webinar. So because mid-infrared photothermal is based on visible photothermal, I would do a comparison of these two modalities. Though the principle is the same, but the details are quite different. Invisible photothermal is based on nanoparticle, like gold nanoparticle, nanorods, and based on the thermal lengthening effect, heating of the medium. In mid-infrared photothermal microscopy, the object is molecules, and the particle or the subject is much larger. So in this case, the mechanism is through the scattering of the particles and under the modulation by the mid-infrared absorption. So for details, there are actually two very excellent review articles. One is the SDS Nano paper by Michel Ori group. And a few days ago, we wrote a review in Science Advance to present this mid-infrared photothermal microscopy. We have done a simulation to show the thermodynamics of a particle under the IR pulse excitation. You can see here that the thermodynamics rising and the thermal diffusion depends on the particle size. So for a smaller particle, like a 300 nanometer, you would need a much shorter pulse on the nanosecond scale to get enough signal. This also depends on the substrate that you use, and also depends on the medium you use. So this impacts the signal level and the contrast. In 2016, in our first MIP microscope, we used this QCL laser for IR excitation. and we use the MCT for power normalization at each wave number. In the microscope, we use the dark field geometry to measure the scattering modulation, and we have some electronics to extract the signal only at the IR modulation frequency, which is the representation rate of the QCL laser. So initially, we actually, this is for us, this is a high-risk project. We did not expect too much. But to our surprise, that when we measure the MIP spectroscopy, the spectral profile is, we can reproduce the FTIR profile, but with even a better line shape, because this is a background-free technology. Also that the sensitivity, we can reach 10 micromolar for CO bond. This is beyond the Raman spectroscopy limit. We can reach sub-micron resolution, which is close to the diffraction limit of the visible beam. So this is a pump-probe approach. In the scanning mode, it's like confocal. You can scan this layer by layer and do image 3D reconstruction. So this is how we produce this chemical bond map of a living cell with sub-micron spatial resolution. So since then, there are many various configuration has been developed for this scanning-based MIP microscope. So in this setup, we use IR and visible co-propagation and do forward detection using dark field. We also build a epi detection, the signal bounce back. So this allows us to visualize the molecule in the tablets. But also this builds the foundation, right, for applying IR to do in vivo applications, which is not possible with FTIR method. The Heartland group in here again in US built this counter propagation geometry. So this allows the use of a high NL objective. So this can even further improve the spatial resolution down to 300 nanometer. And based on this geometry, we have developed a method we call iRaman. It's virtually IR plus Raman, because the same visible beam can do Raman spectroscopy. So you can do a IR photothermal spectroscopy and IR Raman spectroscopy at the same spatial resolution. And because IR and Raman are complementary to each other, so this allows comprehensive chemical analysis. So here is the story that I would love to tell you. In 2016, September, we published a paper in Science Advance. Then I gave a speech in SAIC's meeting in October. And after my presentation, there are two gentlemen came to me. One is Dean Johnson and the other Roshan Shetty. And they told me that they want to convert this method into a product. And that's the first time I realized that the business people can be faster than scientists. In about 12 months, they announced this Mirage, and now it's being used by many groups and through the photothermal spectroscopy cup. Now back to research. So what we did is fill the gap. So in fMIR, we have nanoscale resolution, but slow speed. In QCL-IR provides high speed, but low resolution. What is this optical photothermal method fill the gap between these two modalities? But one mission of science is that to break the trade-off. So we ask the question, can we break this trade-off? Can we reach high speed and high resolution photothermal imaging? And the solution to this question is we do wide field. So in the scanning approach, there is a mismatch in the focus size because the visible focus is much smaller than the IR focus. And this is the same problem in fMIR. But with the optical method, we can overcome this difficulty through wide field illumination, both IR and visible. And we can do visible detection through a simple CMOS camera. So if you ignore the IR part, this is a typical iSCAT microscope. But with IR excitation, we can add the chemical information to this scattering microscopy. But here we do need an elevation because the camera speed is on the kilohertz while the laser is on the megahertz. So we do want to synchronize at the single pulse level, the pump, probe, and the camera exposure. So in the hot frame, we can average many pairs of pump probe signal. And in the cold frame, we turn off the IR and get the cold image. And the difference between hot and the cold, we get the mid-infrared photothermal contrast. So we call this a virtual locking camera. This was done at Purdue through collaboration with Ali Shakuri. So in this method, essentially the speed is half of the camera speed. So the camera is 25 frames per second, and we measure hot and cold and do the difference in real time. We can see the IR contrast. And if we average, and you can get a very high signal to noise ratio. But more important that this still maintains the very high spatial precision because this film or the particle on the substrate, silicon wafer substrate, so there is a very quick thermal diffusion. So this give us the submicron but high throughput IR imaging. So we have a follow-up study now is try to further enhance the contrast in this wide field MIP microscope through a pupil engineering. So at the Fourier plane of this wide field microscope, we add a pupil mask. So this pupil mask detect the scattering, but block most of the reflection photons. This is an intrinsic limitation in a wide field microscope because I can show you here that in the wide field, in bright field, the cold image, you have the particles, but there are a lot of reflection from the substrate. And these reflect photons bring the short noise to the image, right? But if you use a dark field, you remove that, and now the contrast or signal ratio is much better. So this allows us to do a single particle analysis, but with much improved chemical contrast. So in the review article, we summarize the mid-infrared photothermal effect and different ways to detect this MIP effect. In the first paper, we use dark field geometry, and also we mentioned the interferometric scattering in the wide field manner. So there are other group, Nihon Wang in Caltech, using this Gulason parameter to photoacoustic. Also a group in Germany has done this photoacoustic detection of the mid-infrared absorption. But there's another way using the optical phase detection. So what is this? So theoretically, the phase, optical phase depends on, through a sample depends on two parameters. One is the refractive index, and the other length. And this is the foundation of the phase image. But when you have a temperature increase, there's a change in refractive index delta N and the physical length delta L. So you put together, you can write the equation that delta phi is proportional to the absorption. So this simple theory shows that we can measure the phase to measure molecular spectroscopy. So this is very interesting. So the Itaguchi group also did a very nice work in this area. So so this was before I moved to Boston. There's a pioneer in Midwest called Gabby Popescu. He had this diffraction phase microscopy. So it's only 2-hour distance between Purdue and Bernard-Champaign. So we drove there and learned his diffraction phase microscopy. What we measure is the interferogram. And when you use the IR shine, you induce an additional phase shift in the interferogram. So that's very interesting. We measure phase shift, and then we compare the difference. We get the chemical phase. And by scanning the IR laser, we can do the IR spectroscopy. So this paper was selected to be the Microscopy Today Innovation Award 2020, because it addresses a fundamental issue also in phase microscopy. So phase microscopy does not provide chemical information, and IR excitation provides one way to address this problem. So I think there's a lot of potential in this direction. So here are some proof of concept data in this paper that amazingly that we can see the phase change by single IR pulse. This is one by one, and then you see a decay. And in the spectral domain, you can measure the phase, and you can get exactly produce the IR spectroscopy. And of course, you can, if you get a liquid-liquid interface and you tune this oil and DMSO and you tune to each molecule, you can reverse the contrast and you tune off, the contrast is all gone. And in cells, we can measure lipid, also intracellular features between the DNA band. So there are, so this provides potentials, and I think the future trend is convert the 2D into 3D and then do the 3D chemical phase imaging. So with this, I try to summarize that this technique provides sub-micron spatial precision, large cross-section in the fingerprint, and also it's applicable to liquid samples or living cells. So this opens many opportunities through the cancer, neuroscience, chemical histology at the super resolution and the drug distribution, antibiotics. So there are a lot of work has been done. Actually, one thing I would acknowledge, because this is commercialized, so this allowed even broader applications. Here I just showcase a few examples. So this is an example of imaging lipid and protein C. elegans. This was definitely not possible if we do FTIR. But now we can see the individual lipid particles. This image is as good as SIs, but with IR excitation. Because lipid has CO bond, protein, and the water, they have different profile. So you can separate them. You can do drug imaging. This, if the drug has a different signature over endogenous molecules, so you can detect the position of drug molecules in tissues. Also, you can see drug in the tablets. So this is using the backward or epi detection. So you can see this. This is Tylenol tablets, and we can see the API and also excipients using the backward geometry. But now with much enhanced spatial precision, we can study single particles. So one important thing is bacterium. And so this is S. aureus, which have the diameter about 1 micron or smaller. And now with spatial resolution 300 nanometer, we can see these single particles based on the signal from the protein amino-1 peak. So these are the particles they put on the cover slip and they dried on the IR transparent cover slip. The spectrum of MIP exactly consistent with FTIR, but the FTIR is not on single bacterium. This is millions of bacterium make a film, and you can measure FTIR. But with MIP, you can do single cell level, and of course, you can use the same visible to do Raman spectroscopy. Here you can see Raman is more sensitive to CH, but IR is more sensitive to the fingerprint regime. You can also do this in the mammalian cell. These are the lipid in the mammalian cell. And again, you can see the IR and the Raman are complementary to each other. IR is very sensitive to fingerprint region, the CO bond, while the CO bond is very weak in Raman spectroscopy. Raman is very sensitive to CH2. So again, this is a very nice platform that you can couple IR and Raman together, which has never been done before on a single platform. Because of this sensitivity, we can do functional analysis. So here we ask that what happens inside the bacterium if the S. aureus is exposed to antibiotics. In this case, is erythromycin. So this one inhibit ribosome. So theoretically, it should reduce protein synthesis. But meanwhile, that the untranslated RNA will accumulate. So suppose we can see more nucleic acids and less protein. So we did a single cell spectroscopy in IR photothermal. You can see the amide-1 band decrease, amide-2 band decrease, and the phosphate peak increase with super high signal-to-noise ratio. And this is taken in 1 second. You can scan like 800 wave number and get this high quantity. In comparison, we use the same visible power and you do Raman, we barely see anything. That's a very good demonstration that IR has much higher cross section. So in consequence, with IR, we can see this difference response to the drug, while in Raman, we barely see not much. So because the sensitivity, we actually can do a single virus detection. This virus is about 150 to 100 nanometer in size. So if we purely do scattering, we would not have enough photons. So the idea that we do interferometric scattering. So this is exactly the principle of iSCAT. And now we use an IR pump to modulate this interferometric scattering. So with this, you actually can we can get the fingerprint of a single virus, and the fingerprint is different from different virus. And this may have lots of potentials, but in any way, this is not possible with spontaneous Raman if we don't use plasmonics, or with the traditional FDR, we would not imagine that can do it. So this is all a scattering-based approach. But finally, I want to show you a couple of slides, show you that we can thinking out of the box again. So the method is called fluorescent detected MIP microscope. The rationale behind this is that the thermal sensitivity of fluorescence is much bigger than scattering. Fluorescence emission intensity can be 1% per degree, while scattering is 0.1% degree. So it's 100 times bigger. Right? So if we, under the assumption that we have enough fluorophores in the sample, then we can monitor the fluorescent intensity modulation rather than monitor the scattering. And this should get a much higher signal-to-noise ratio because the modulation depth is much bigger. So with this, we built a setup. This still QCL laser and with the photodiode to measure scattering. But when we can use the PMT to measure fluorescence, of course, we have to label the sample. So we got some preliminary data. And so this is SRs labeled with rhodamine or SIF2. And you can do fluorescent image, but also do this fluorescent enhanced or detected MIP. So, and you can scan the laser, get the fingerprint. We can also do scattering. And scattering is interesting. Scattering is more sensitive to the edge. We see a donut shape, but fluorescence is from the cell body. So it's more mimic. Fluorescence is incoherent. Right? So this is two things that these two modalities that they have quite different. But they tell the same content. Is the largely dominated by the protein content and the phosphate peak in the cell. But the advantage of fluorescent detection is more clear when you do another advantage I will show you here. Another advantage is fluorescence can give additional contrast because fluorophore may label different organelles. Non-red will label the membrane, and rhodamine 103 would label mitochondria. So you get the additional information while you do the vibrational spectroscopy. So in principle that we could, using for example, GIP to label a specific protein and then detect the secondary structure of the protein. When we go to the wide field, the sensitivity is much obvious because in wide field, we use a CMOS camera. We don't have much photons at each pixel. So in this case, that if we do a scattering-based approach, the contrast is limited by the reflection or the short noise from the background. But fluorescence is the top rule of fluorescence is background free, right? So this is intrinsically short noise limited. It's on a new frequency, so it's give a much higher contrast. And you can see this is a wide field. So what we do is we record hot, cold. So one ion on, ion off, and then the in fluorescence, the modulation is 2%. In scattering, we barely see anything. We had to average millions of thousands of frames to get to the contrast because the difference is 0.01%. So with this, will stop here. So our group in Boston University Photonics Center, if you are in the Boston area, you are welcome to visit us. Thank you very much. I'm happy to answer questions.
Thank you very much, Professor Cheng. Thank you, Ji-Xin. You are welcome to ask questions either by writing in the chat or by asking directly. So I see no questions yet, but so I may start maybe with the first question. You showed us very impressive images of the chemical composition of and for example, let's talk about this bacteria with the proteins and RNA. So it's very nice to have this chemical resolution. How about the spatial? So you didn't explain so much the spatial distribution. So can you see differences in the distribution of these compounds throughout the cell?
Oh, that's a good question. Yeah, I think we can in the mammalian cell because the resolution is 300 nanometer. That's the diffraction limit of visible beam. That's not enough to see the distribution inside a single bacterium, which is very small.
Too small,
right?
Yeah.
But the possibility exists that we can break the diffraction limit of visible. That can even go further.
Okay. Thank you very much. Are there more questions? I see. Yeah, Daniela Teuber is from Jena.
Hi.
Can
we met
you
in
please
Lund
ask?
once with Ivan Shebilikin. So,
yes.
yeah, I have two questions. Thank you very much for this interesting and fascinating presentation. So I have two questions. One is we have this instrument freshly in our institute, and I'm one of the scientists using it. So my question would be, what type of substrates are you using for your cell investigations?
That's a very good question, right? So substrate is very important. We're using usually two kinds of substrate. One is that if we do transmission model, we're using calcium fluoride. And if we do reflection model, you can simply use a silicon wafer, and that's very cheap and high reflection. Yeah.
Okay. And the other question was, well, we started with tests, and we were using polymers, of course, and so the sensitivity is in the manual of the Mirage says it's like 200 nanometers film thickness from a polymer film. So what's about different amount of material in the bacteria? Can you estimate what you need to get a signal?
Get a signal from what? From the film or from the bacteria?
From, let's say, a cell or a bacteria.
We have, I think we have enough signal from bacteria. We can even see virus. You mean what parameter we need?
Yeah, no. I think you get a signal, but to discriminate protein and sugar. So if there's just 3 sugar molecules, you won't find it. So what amount per space, or can you give some quantitative estimate?
I see. That's a very good question. Indeed, we want to do a multi-contrast imaging. The key is that you need to get to the right laser to do it. In our case, actually, in this QCL laser, the energy in this CO bond is not very high, so that limit sensitivity. So if you find the right laser, you can do it. There are OPO based. QCL is most convenient.
I know. Okay, so the sensitivity depends on the power of the incidence.
Yes.
Okay. But don't you heat it up too much? Boil it?
No, actually not. We calculate the temperature rise. It's about less than 4 degrees.
Okay.
And you can get a lot of signal already.
Less than 4 degrees in biomaterials.
Yeah, because you think if the limit is 0.01%, that's 10 to minus 4. 10 to minus 4 is pretty high, actually, because in SI it's 10 to minus 6. So this is still much more sensitive than similar.
Yeah, true. Okay, so thank you very much for your explanations.
All right, thank you very much. We have another question by Ming-He Lee. So maybe go ahead.
Thank you. Nice talk, Professor Chen. I have actually a question about sample preparation. So my question is about the thickness of the sample. Since like the IR pulse cannot penetrate so like large distance, usually it penetrates about several micron, like no more than maybe 100 micron. So if you are observing a cell which is probably thicker than 100 micron, how could you get the signal? If you could only get signal from the surface, maybe the top surface of the cell, how could you probe the cell?
So actually 100 micron is a lot thicker. The cell is only 10 micron in thickness. So cell has no problem. Now, this image shows you that we can actually see the C elegans. The C elegans, the diameter is about 50 to 100 micron. So you can look into we checked the penetration depth if you avoid the water peak, you can reach 80 micron. So that's pretty much a lot so you can do the tissue histology, right? Tissue slice, no problem. And there are ways we think that there are ways if you can replace the water with other medium, you can go much deeper. But overall, this method is good for single cell analysis, for tissue slice, and I believe it's also good for in vivo application.
Thank you.
Okay.
Thank you. Next question is by Chia-Lung Xie from Taiwan.
Hi, can you hear me?
Yes.
Nice talk, Ji-Xin. You mentioned in your talk several times that when you do this dark field mode or even fluorescence mode, MIP, the background is lower, so that helps you to improve the signal to noise ratio. That I can understand because the shot noise gives you a background when the light is too strong in the background. But then when you talk about the virus study, you also mentioned the virus is very small, so you need interference to see the virus. That I also understand, but these two things are kind of confusing to me. So the way I see it, is it correct to consider the signal of the thermal lens, but not the scattering image of the sample? So how should we consider the sensitivity between these two different modalities?
You asked an excellent question. Indeed, that there are two opposite approach. One is reduce the background, and second is harness the background in the virus detection in the photometric scattering. When the particle is so small, I think interference with the reflection is definitely the way to go. And in the case of the single virus, maybe fluorescence is not a good approach because, as I mentioned, that when you do fluorescence, you need a certain number of dye molecule in the particle. If you only have 1 or 2 dye molecule, then that will limit the signal. the dark field approach is more useful for larger particles. And when you go to smaller particle, we wouldn't have to use the interference approach.
So that's my question. I'm not sure I understand why. Suppose we have the same amount of thermal energy created by the photothermal, and then that means we have the same amount of scattering signal from the thermal lens. Is it still true that the dark field will give us better, or which one will give us the better SNR? Or is it?
Yeah, sure. In the very small particle like a virus, if we do dark field detection, because the scattering from a single virus too little, we don't have photons, so we have nothing to detect. Yeah.
I see. So just the thermal lens is not enough. You need to somehow to have a scattering or reflection signal to interfere with the thermal lens.
Yeah.
I see. Thank you.
Thank you very much. I think we can take the last question by Ji-Xin Cheng. So please go ahead.
Thank you, Howard. Thank you, Ji-Xin, for this wonderful talk. You show a series of powerful tools, and I'm wondering if that's feasible to develop this into portable and user-friendly tools, so more people can use it, or even for POC devices.
That's a good question. Excellent question. I think I mentioned that we are very lucky that after my presentation, we met this gentleman, Roshan Shetty, and he now is as a Mirage, the commercially available. Actually, most applications are done by the customer Mirage. They are faster than I do, so you can look into this. And I think you probably will give a talk as well. Indeed, that you mean the portable device?
Even better, if it becomes portable.
Portable is also doable. Portable is definitely doable. You think about this, can be fiber-based, so you can do in vivo surgery guidance. I think this is a great direction, because you do IR absorption and the visible scattering. So definitely, that's a very good direction to go here.
I think there's a company in Germany who's selling glucose monitoring devices, which is portable based on that kind of principle. I mean,
it's a photoacoustic, right? That one is photoacoustic.
No, I think it's infrared photothermal.
Oh, photothermal based. Yeah.
So yeah, I think I just saw that recently. Yeah.
Thank you.
Thank you, Frank.
I have one slide. I'm sorry, I forgot to show. I wanted to showcase this. There's a chemical imaging golden conference which we initiated this year, but due to pandemic, it put to 23, and some of you are speakers in this. So I hope that please join this conference in 23 summer. Thank you.
All right, thank you all very much. It was a very fascinating talk and lively discussion. So I think it's now time to move to the second talk, and I will leave the word to the chairman of the second session, Frank Zichos. So goodbye all.